Okay, let's unpack this one. It's a really fundamental cosmic riddle, isn't it? Where did all the heavy stuff, like gold, actually come from?
Exactly. We get how stars cook up elements, up to iron. That makes sense.
Right, stellar fusion.
But beyond iron, all those heavier elements, that's been a huge puzzle for a long time in astrophysics.
Because the early universe was, well, pretty simple, elementally speaking.
Yeah, almost entirely hydrogen and helium with just a tiny trace of lithium. Everything else, all the complex matter that makes up, well, us, planets, everything, it had to be forged later.
And figuring out how those first heavy elements got made and spread around, that's the key question.
It really is. As Anirudh Patel, who led this recent study, put it, it's a pretty fundamental question. It's a fun puzzle that hasn't actually been solved.
A fun puzzle. I like that.
Yeah.
And for you listening, especially if you're prepping for exams like the UPSC, understanding this kind of cosmic origin story is pretty foundational.
Absolutely. It ties into everything, how stars work, how galaxies evolve, even where the materials on Earth came from. It's core knowledge, really.
So today we're diving into some fascinating new research. It was published in the Astrophysical Journal Letters, and it digs into old data.
Yeah, that's the cool part. Archival data from NASA and ESA telescopes, some of it 20 years old.
Looking at it with fresh eyes, and maybe finding a surprising source for a chunk of these heavy elements way back in the early universe.
It really shows you the value of going back to the archives sometimes. You never know what might be hiding there.
Okay, so our mission today, figure out this potential new origin story for heavy elements. Let's start with the main suspect in this new study, magnetars.
Right, so first, neutron stars, we know those, right?
The collapsed cores of massive stars after they go supernova, insanely dense.
Like unbelievably dense. A teaspoonful would weigh billions of tons here on Earth. It's hard to even picture.
Mind-boggling. And a magnetar is.
A magnetar is basically a neutron star, but with a magnetic field that is just monstrously powerful.
How powerful are we talking?
We're talking trillions. With a T, trillions of times stronger than Earth's magnetic field. It's almost unimaginable energy.
Okay, wow. Trillions. So what do these supermagnetic stars do?
Well, sometimes they have these violent events called starquakes on their surface, kind of like earthquakes, but, on a neutron star.
Which must be intense.
Oh, yeah. And these starquakes can trigger these enormous bursts of high-energy radiation. We call them Magnetar giant flares.
Giant flares, are they common?
Actually, no, they're incredibly rare. We've only definitively seen 3 in our galaxy and the nearby Large Magellanic Cloud, maybe 7 others further out.
So rare but powerful.
Hugely powerful. Powerful enough that flares happening thousands of light years away can actually affect Earth's upper atmosphere when they hit us.
Whoa. Okay, so we have these incredibly magnetic neutron stars having rare, super powerful flares. How does that make gold?
Ah, right. This gets into the mechanism. It's thought to involve something called the rapid process, or the R process.
The rapid process. Okay, break that down.
So imagine the environment during one of these giant flares, especially if it rips material off the neutron star's crust. It's incredibly hot, incredibly dense, and just flooded with neutrons.
Okay, neutrons everywhere.
Exactly. Now, atomic nuclei, the cores of atoms, are made of protons and neutrons. The number of protons defines the element, right?
Yep, iron is iron because it has 26 protons.
Right. Now, in this neutron-rich soup, lighter atomic nuclei can just start rapidly capturing these free neutrons, one after another, really fast.
So they get heavier, but they're still the same element.
Initially, yes. They become heavier isotopes of the same element, but they often become very unstable with all those extra neutrons.
Makes sense. Too much baggage.
Kind of. And to become stable again, one of the captured neutrons can undergo a type of radioactive decay where it transforms into a proton.
Ah, so it changes the number of protons.
Precisely. And if you change the number of protons, you change the element. So an atom captures neutrons, becomes unstable, a neutron turns into a proton, and boom, you've climbed one step up the periodic table.
So like silver could capture a neutron, decay, and become cadmium.
Exactly that kind of process.
Yeah.
Or, as the sources mention, maybe even gold becoming mercury. And if this happens rapidly, capturing many neutrons very quickly before they decay.
You could climb really high up the periodic table, making things like, I don't know, Uranium.
Potentially, yes.
Yeah.
You could synthesize the heaviest elements that exist. It's like a cosmic alchemy powered by these extreme conditions.
That is wild. Now, I remember hearing about heavy element creation back in 2017. Wasn't that about neutron stars merging?
Yes, the kilonova observation. That was huge. LIGO detected gravitational waves from two neutron stars colliding, and telescopes saw the aftermath.
And they confirmed heavy elements like gold and platinum were made.
They did. It was direct proof that neutron star mergers are one place where the R process happens and creates these elements. Absolutely fundamental discovery.
But I sense a but coming.
Well, the but is about timing. While mergers definitely make heavy elements, astronomers think they might happen, generally a bit later in cosmic history.
So maybe not early enough to explain the very first heavy elements found in the oldest stars.
That's the potential issue. We see evidence of heavy elements in very ancient stars, and it's not clear if enough neutron star mergers could have happened that early on to account for them.
Which brings us back to these magnetar flares.
Exactly. The idea explored in this new research is that these giant flares could blast material off the neutron star's crust at high speed.
And that ejected material would be the perfect place for this rapid process.
That's the theory. You get the incredibly high temperatures, the density, and crucially, that flood of neutrons needed to rapidly build up heavy nuclei. It could be an alternative, maybe earlier production site.
So how did they find evidence for this? You mentioned old data.
Right, this is the clever part. The team, led by Anirudh Patel, went back to data from a really powerful magnetar giant flare that happened way back in 2004.
20 years ago.
Yeah. It was observed by several telescopes, including ESA's integral satellite, which NASA contributed to. Now, the main initial burst of gamma rays from that flare was understood, but apparently there was this fainter, sort of lingering gamma ray signal after the main burst that nobody could really explain back then.
A little lift of a glow.
Something like that. Eric Burns, one of the study co-authors, said, "It was noted at the time, but nobody had any conception of what it could be. Just an unexplained blip in the data."
A cosmic cold case.
Pretty much. And then, completely separately, theorists like Brian Metzger and his team started working out predictions. They calculated what the gamma ray signature should look like if a magnetar flare was actually forging and ejecting heavy elements via the raw process.
Okay, so they had a theoretical fingerprint.
Exactly. And when Burns and Patel compared Metzger's theoretical prediction to that unexplained signal from the 2004 flare data,
Don't tell me.
it was a near-perfect match.
No way.
Yes. Metzger even mentioned that Burns initially thought they were kidding, pulling his leg, because the match between the theory and the old unexplained data was just so incredibly close.
That's amazing. A 20-year-old mystery potentially solved by a new theoretical model. Science at its best.
It really is. And they didn't just rely on integral. They also pulled in data from two NASA missions, ARESI and WIND, which were actually designed to study the sun, but also happened to see the 2004 flare.
Cross-referencing the data.
Right. And those observations helped confirm the characteristics of the signal, adding more confidence to the idea that they were seeing the signature of heavy element creation.
So what's the bottom line? How much gold, how much uranium could these magnetar flares actually be responsible for?
Well, based on this one event and estimates of how often these giant flares might happen, the study authors calculate it could be quite significant.
Like,
They estimate that magnetar giant flares might have produced up to maybe 10% of all the elements heavier than iron in our galaxy.
10%. That's not insignificant at all.
Not at all. It implies that, as they say, the first gold could have been made this way. It provides a potential explanation for those heavy elements in the very early universe.
Wow. So for you listening, especially with UPSC in mind, this potentially shifts our understanding of where the building blocks of, well, everything complex actually originated.
It adds a really important piece to the puzzle of cosmic chemical evolution.
The first gold. That phrase really sticks with you. Thinking the gold in, jewelry or electronics might trace its origins back to these unbelievably violent explosions on hypermagnetic dead stars.
It definitely puts everyday materials in a new cosmic perspective.
Is this the final word then? Or is there more research coming?
Oh, definitely more research needed. This is based on analyzing one, albeit very telling, event from the archives. Scientists are already looking at data from other recorded magnetar flares to see if similar signals are there.
Makes sense. Check other cases.
And there's excitement about future missions. NASA has one called COSI, the Compton Spectrometer and Imager, planned for launch in 2027.
What will COSI do?
COSI is a gamma ray telescope. specifically designed to get a wide view of the sky and study these kinds of energetic events. The hope is that it will be sensitive enough not just to see the glow, but potentially to identify the specific spectral signatures of individual heavy elements being created in these flares.
So it could actually see the freshly made gold or platinum.
That's the goal. It could provide much more direct smoking gun evidence for this process if the theory holds up.
That'll be exciting to watch. It really connects the dots, doesn't it? These extreme astrophysical events creating the raw materials for technology.
Yeah, Patel mentioned that too, how cool it is to think that some of the stuff in my phone or my laptop was forged in this extreme explosion.
It connects the absolutely vast with a very tangible. Okay, so let's wrap this up. For you, our listener, maybe jotting down notes for UPSC or just fascinated by the universe, the key takeaway here is that magnetar giant flares have emerged as a really strong contender for creating a significant fraction, maybe up to 10%, of the heavy elements like gold, especially the ones formed very early in cosmic history.
It's a compelling alternative or perhaps complementary process to neutron star mergers, helping explain the full inventory of heavy elements we see.
And it's a fantastic example of how revisiting old data with new theories can lead to major breakthroughs. The answers might already be sitting in our archives.
Which is exciting for future discoveries, too.
Right. So here's something to think about, a little provocative thought for you. We talk about gold or uranium having these incredibly violent exotic origins in magnetar flares or neutron star collisions. What other seemingly ordinary parts of our world, maybe even fundamental laws or particles, might have origins that are equally bizarre and extreme, secrets still hidden in the cosmos or in the data we've already collected?
That's a great question to ponder. It highlights how much we're still learning about the universe's history and the fundamental processes that shaped everything around us. There are likely many more surprises waiting.
Absolutely. So we really hope this deep dive sparked your interest. If you want to understand more about how the universe works, astrophysics is just full of these amazing stories.
Keep exploring.
And if you found this useful, especially for your studies, please do give us a like, subscribe to the channel, and definitely drop any questions you have in the comments below. We do read them.
Yeah, we appreciate the engagement.
And just to be clear, all the details we discussed today are based on information released by NASA's official website, covering the research published in the Astrophysical Journal letters.
Solid sources.
Definitely. Thanks for joining us on this deep dive.